Let us move on to the second topic, review of basic thermodynamics of ideal gas mixtures. Okay, now a definition of ideal gas basically comes like this. Okay, the fundamental properties pressure, volume and temperature. Okay, so they are related by what is called equation of state. So any equation which relates these three properties, we call it equation of state. And ideal gas equation of state is very simple in nature. For example, I can write ideal gas equation of state as PV equal to RT. So here pressure into volume will be equal to RT, where this volume is specific in nature. A specific volume, the total volume capital V divided by the mass is small v. It is a specific volume meter cube per kg. So ideal gas, when you say a gas behaves like an ideal gas, then this obeys this particular equation for its PVT relationship, where this R is called a specific gas constant. Okay, so we can write this equation in several other ways. So, but the main content here is when a gas behaves like an ideal gas, then this simple PVT relationship holds good. But in general, no gas is going to be a perfect ideal gas. So no real gas will follow the above equation of state in all range of temperature and pressure. Only under certain conditions it will behave like an ideal gas. Okay. So what are the conditions? Okay, now when you have very high temperatures, low to moderate pressures, then we will get densities to be at a low to moderate value, so lower densities and so on. Okay, now coming to our combustion products. Combustion products are at very high temperatures, and even if pressures are somewhat low to moderate, the densities are not going to be high. When the gas density is very low, then the molecules are not very close to each other always. Okay, so they hit with each other and move apart, and they are not always not very close to each other. When they are very close to each other, what happens is, when they are very extremely close to each other, then they repel, the molecules repel each other. As the separation distance increases, basically what happens is the repulsive forces decreases, and it becomes an attractive force, and that becomes a maximum at a particular separation distance. And as the separation distance increases, say I am saying average separation distance that is increased, then what happens is the attraction forces or the repulsive forces and attraction forces or we can say intermolecular forces between these two molecules tends to 0. Under those conditions, a gas behaves like an ideal gas, obeying this equation of state. Okay, so all the gases are real in nature, and they will not obey this under every circumstances. Only when the densities are very low. That is accomplished when temperatures are very high or pressures are low to moderate, very not extremely high pressures. So low to moderate pressures and high temperatures, you can see that the densities are low enough so that the intermolecular forces are negligible. Okay, so in that such cases, basically a gas behaves like ideal gas, and if this gas is not a single gas but mixture of gases, and the mixture itself will behave like an ideal gas. Okay, so combustion products are mixture of several gases, but due to the high temperature prevailing there, the mixture density will be low enough so that the combustion products can be qualified as an ideal gas mixture. Okay, so in an ideal gas mixture, all the gases are ideal gases, and they obey this equation of state given by PV equal to mRT, P capital V equal to mRT or P small v equal to RT. So this is the introduction to ideal gas. So in our course, we are going to deal the combustion products as or even reactants for example, because we are not going to work with the extremely high pressures, so the densities are lower enough, and we can assume that the reactants or products, any mixture for that sake, will behave like an ideal gas. Okay, so according to Avogadro's hypothesis, 1 kilomole Okay. So, or M, capital M kg of the gas at standard atmospheric pressure of 1.01325, it is called 1 atmosphere pressure, 1.01325 bar, and the temperature of 273.15 Kelvin, 0 degrees, occupies same volume. So, this is given by 22.416 meter cube. Okay. Now, P times capital V will be equal to this M, which is actually the molecular mass, times R times T. Okay. So, now this holds good for ideal gas. So, this is the equation state. I am just trying to write in this way. The quantity MR is called the universal gas constant or suffix U, and it has a value of 8314 joule per kilomole Kelvin. Okay. A specific gas constant can be written as R equal to R suffix U divided by the molecular weight M. The molecular weight, it has a unit of kg per kilomole. So, when you substitute here, you will get the universal gas constant as a unit of joule per kilomole Kelvin, and if you divide that by the molecular weight, you will get a specific gas constant which has an unit of joule per kg Kelvin. Okay. So, you can write the ideal gas equation of state in terms of universal gas constant given by P times total volume V equal to N, where this N is the number of moles of the gas into universal gas constant times temperature. PV equal to N R suffix U times temperature. This temperature should be in Kelvin. Okay. So, that you have to remember. So, we can write the equation of state in several ways. So, as I told you, we can write, so this N is the number of moles occupied by a particular gas or gas mixture, total number of moles occupied by the gas mixture, and this is the pressure exerted by the mixture, and volume occupied by the mixture is V, and this is temperature of the mixture is capital T. So, this is the way we write. We can now, if you want to change it to mass basis, then you can we can write this as P V equal to mass times R times T. So, this is the another way to write the equation of state. So, now divide this mass to the volume, we can write P V by M equal to RT, which implies P V equal to RT. That is what we previously wrote. So, this is the equation of state, which is very simple in nature, and ideal gas alone obeys this under certain circumstances in the range of temperature and pressures. So, where the densities are low enough. So, this is the there are several ways to write the equation of state. We can also go one more place. We can write this as say P V by N equal to R, sorry, yeah, equal to R U times T. Now, this V by N meter cube per kilomole. So, this is molar specific volume. So, this can be written as PV bar equal to RUT. So, several ways you can represent. So, this is molar specific volume meter cube per kilomole, or you can also do this. See, I will write here. So, P this V I will take to other side. So, N by V RUT. Now, this N by V is kilomole per meter cube. This is the concentration. So, this can be written as concentration times RU times T. So, this is C is concentration, that is number of moles which is occupying a given volume V. Similarly, I can write for this as, so P V will take to other side equal to M by V times R times T. So, that means this M by V is kg per meter cube, that is density. So, it is equal to density rho, R is the specific gas constant, and T. So, there are several ways of writing the equation of state. So, now here you can see P pressure equal to rho RT, here pressure equal to C into RU times T, concentration. So, whenever you write the equation in molar basis, you will see that the universal gas constant appears. whenever you write in mass basis, then the specific gas constant will appear. Okay, so this is the way we can write. So the ideal gas, each ideal gas in a mixture or the mixture itself will behave like an ideal gas and obey these equations of states written in any form. Okay, now what about other properties? So now we have connected three important properties, namely pressure, volume and temperature, and a simplistic equation like this: PV equal to MRT or PV equal to NRUT, etc. can be used to relate pressure, volume. So any two properties, if we know, the third property can be found out and so on. So this is the way you relate the pressure, volume and temperature, three fundamental properties. Okay. Now coming to other properties like internal energy, enthalpy, etc. For ideal gas, again we have lot of simplifications. Okay, so normally if you take internal energy, basically is not only a function of temperature, it is also a function of volume. Okay, so internal energy can be written in terms of, say for example, I can write here U will be a function of V comma T. Volume and temperature, any two properties can be used to write this. So this means that when you want to find the change in U, you have to write this as so like this, correct. So you have to see that du is dependent on both the rate of change of u with respect to V when temperature is held constant times dV and the rate of change of u with respect to temperature when V is held constant times dt. So now if you write like this, you will see that actually for every real gas this is what is obeyed. However, by Joule's experiment, so Joule has considered constructed experiments and he has considered several materials and several conditions, and he found that the internal energy for an ideal gas is dependent only on temperature. That means for ideal gas, U is a function of T only, not V. So this is one of the important aspect of ideal gas. One more simplified equation you get. So you don't need to have a partial derivative there. So now you can very easily write that U is a function of T only. So any change in U will be du by dt. That's it. So we can find that using that. Similarly, enthalpy is a derived property, U plus P times V. You will note that U and this PV can be now expressed in terms of equation of state. Say for example, I will take the molar based N times Ru times T. So He will be equal to U plus N times Ru times T. That means since U is a function of temperature alone, now H also will be a function of temperature alone. Okay, or in other words, we have to write H as a function of temperature plus pressure. Actually, for all other gases, you can write H as a function of P comma T. But now you can see that by Joule's experiment for ideal gases, the dependence of enthalpy on pressure is not there. So enthalpy will be dependent only on temperature. Similarly, internal energy is only function of temperature. So you can evaluate that. So now if you write H or even U, okay, as a polynomial of T. So we know that it's only a function of temperature. Let us consider a polynomial dependent of U. So for example, U, same thing you can write A plus BT plus CT square and so on. I can write this. So now just add the other term NRUT here. If you add, then that will be absorbed with the another coefficient B. So H also can be written in terms of this polynomial. Now finding the specific heats, okay, specific heat at constant volume or specific heat as the constant pressure basically can be found by these equations. Okay, for example, the specific heat itself, okay, Cv is defined as dou U by dou T at constant V. So, this is a specific property. So, specific heat at constant volume is defined as the partial derivative of u. Okay, so this is a term here. See, you can see this in this term. This is a term when you just divide this by mass, you will get the specific heat. So, dou capital U by dou T at V constant volume. When you this U is divided by mass, you will get the specific heat. So, specific heat at constant volume is defined as partial derivative of U with respect to temperature when V is constant. However, for ideal gas, this partial derivative disappears and you write du by dt. Okay. Similarly, H small h is the specific enthalpy. So, capital H divided by mass. So, the specific heat at constant pressure Cp is the derivative of H with respect to temperature. That is, it is an ordinary derivative. We do not need to use the partial. So, as per the definition, Cp is dou H by dou T at constant pressure. Okay. But since H is for ideal gas, H is dependent only on temperature, this partial derivative can be written as the ordinary derivative like this. So, these are called see, these are specific properties and very important for us. For our problems, we have to calculate Cv, Cp, etc. as a function of temperature. So, once you know enthalpy or internal energy return in terms of temperature, we can use that and calculate the Cp and the Cv values, and very important for us to do this. Now, if we do this, Cp minus Cv will be equal to R. Okay, now please understand there are this, when I say Cp and Cv, right, like this, they are mass based quantities. That means the units of this is joule per kg Kelvin. Okay, so I have written here. So, its units is joules per kg Kelvin. So, we can also write in terms of moles, like joule per kilomole Kelvin. Just divide this by the molecular mass. Then, whenever we use molar quantities, we use a overhead bar. So, when I say Cv overhead bar, that means its unit is joule per kilomole Kelvin. Okay. So, that is the way you write. So, now when you subtract Cp to Cv, so Cp minus Cv will be equal to the specific gas constant, because it is written in mass basis. If you do Cp bar minus Cv bar, you get Ru. So, this is molar basis. So, this is the way you write. So, that is what. So, difference between the molar specific heat will give you the universal gas constant. So, the equation of state is simple enough. So, PV equal to nRUT, and even you can see that dependence of internal energy, enthalpy, etc. is only with temperature, not with any other properties like volume or pressure advantage, and Cv and Cp are not partial derivatives of U and H respectively anymore, and they are ordinary derivatives. So, these are the advantages of this assumption, ideal gas assumption, and it is not only an assumption, it actually good enough for our combustion calculations because of the low densities involving high temperatures. Okay, now, yes. So, now a gas mixture we will consider now. A gas mixture under ideal conditions, that means all the constituents of this gas mixture, each and every constituent is an ideal gas. If that is so, okay, so if I have a mixture of say O2 and N2, that is a standard air, it can be taken as ideal gas for practical purposes, because it the temperature is say 25 degrees centigrade and pressure is only 1 atmosphere, very low pressure, densities are not very high. So, its density is say 1.2 kg per meter cube approximately. So, now at this low density, air will behave as an ideal gas. This is because the oxygen and nitrogen both behave as an ideal gas. So, the air itself will behave as an ideal gas. So, when each and every constituent of the mixture is an ideal gas, then the mixture itself will behave as an ideal gas. Okay, now how will you analyze the mixture? Okay, the first one is we have to first quantify the mixture. See, as I told you, now air contains some amount of oxygen, some amount of nitrogen. First of all, we should know what is the amount. So, that is done by two types of analysis. One is called gravimetric analysis and another is called volumetric analysis. Gravimetric analysis are actually some costly devices, but they give mass of each component present in the mixture. Okay. So, for example, if there are capital N components, then by doing a gravimetric analysis, you will get masses of individual components. For example, if M is the total mass of the mixture, then I will get M1, M2, M3 etc. till Mn. If you add up, you will get the M. So, you take a mixture of mass M and subject it to gravimetric analysis, it will give individual components present in that, and the masses of individual components are M1 to Mn, and if you add it, you will get the mixture mass. So, this is obeyed, and you can see that when you divide this by M, okay, this total equation by M, you get an identity. I will come to that next slide. Okay, now from this equation I can define what is called a mass fraction. For example, take jth species, it can be any species. So, take jth species, the mass fraction of the jth component or jth species is mass of that species divided by the mass of the mixture. So, Yj equal to Mj divided by the mass of the mixture M, small m. So, this is called mass fraction. Yi I am using here, Yi or Yj here will be equal to Mj by M, mass fraction of an individual component. So, that is, so we normally deal with the mass fractions, mole fractions, volume fractions, etc. Okay, now similar to the gravimetric analysis, we can also conduct volumetric analysis, which are cheaper actually. Volumetric analyzer is a cheaper analyzer, but it will give volume fractions of the constituents present in this. So, it will take some amount of volume of gas and it will give the volume fractions of the individual the gases present in this. So, this is actually accomplished by having some columns in which a particular gas will be absorbed. So, when the mixture passes through these columns, a particular gas is absorbed in each column, so that we will know what is the volume of the gas which is absorbed. So, eventually you get the volume fraction of the mixture. So, if Vfj, V suffix Fj is the volume fraction of the jth component, then we can add all of this. Okay, for example, Vf1 plus Vf2 so on to Vf capital N. Capital N is the number of the components present in the mixture, will be equal to unity. Okay, now volume fraction I can get. So, that means that by experiments you get a mixture. So, you just you use the mixture in a gravimetric analyzer or an volumetric analyzer, and you can get either the mass fractions directly or volume fractions. Now, we can write the equation of state, for example, as PV. Here I have told you here PV equal to MRT here. So, you can write like this. So, this can be applied to a mixture. So, what is the pressure P here? Pressure exerted by the mixture, volume capital V is volume occupied by the mixture, M is the mass of the mixture, and this R is the specific gas constant for the mixture, and the mixture occupies the temperature of T. So, this I can apply and find some relationship out of this. Okay, now if you have volume fractions, where you will apply that? Volume fractions, because you have another equation which is nothing but PV equal to see PV this. So, for the mixture, pressure is known, total volume occupied by the mixture is known, N is the number of moles occupied by the mixture, universal gas constant and temperatures are known. So, how will you measure number of moles? Okay, so you cannot do this. Okay, so basically volume fraction if you get, what you will do with that? Mass fractions if you get, at least know what I will do is, see I can write this equation and I can take a volume in which for example, I can take only one component and see if the mass of the component is measured to be M1. So, I will try to see how much volume it occupies, how much pressure it exerts and so on for a given temperature. So, I will get some equation for that. So, basically the mass fractions is directly got, so that is easy for us, and all our other properties I will try to correlate in terms of mass fraction itself. Okay. So, that is the important advantage of getting the gravimetric analysis. But when you do a volumetric analysis, how will you translate the volume fractions into mole fractions? See, for example, small n is the number of moles of the mixture, but each and every component can only have some number of moles. And if you add all the masses, you get the total mass of the mixture. When you add each and every number of moles of the individual components, you will get the total number of moles. So can you translate the volume fraction to mole fraction? So that's what the question is.